Hey everybody, I am going to walk us through the virtual lab for RedOx today. I have two screens I'm going to be flipping back and forth from. This first screen is the actual simulation, and this screen is your actual lab that you should be looking at. So I went to this animation site that says it only works in Internet Explorer. I have it up and running. We need to take some data. So I'm only going to write on this page once or twice, and I'm going to let you guys, I'll run through the rest of them, and I'll let you guys decide what's what. So I have silver. This is a chunk of metal silver, and I have hydrochloric acid. I'm going to put the silver in the hydrochloric acid. And what do we see going on? Do I see any reaction at all? I just see the H pluses bouncing off. Okay, so I'm going to go back here and say observations when placing hydrochloric acid, and I'm going to say no, nothing. You can say nothing happened. You can say the H pluses didn't react. Is the spontaneous reaction No. Or is the reaction spontaneous or not? Okay, so I'm going to go back. Now I'm going to try copper. Now I'm going to put in copper. And I'm going to watch those H pluses hit that copper. I don't see them any hit yet. They're a little bit randomized. Some are moving. Oh, there we go. Boom, nothing happens, nothing happens. H pluses hit, but nothing happens. It's kind of funny how this one is all over the place as far as my H plus is not touching. And this one's moving real slow. There we go, some more that are not happening. So copper, again, nothing. Was the reaction spontaneous? Well, no, I didn't see anything yet. Now I'm going to try iron. Let's put iron in and watch what happens when iron hits. Oh, electrons jump onto the H pluses and off come ions. Nice. Now I'm going to go back to the step-by-steps later on in the lab. For right now, we just need to see what's going on. So in this case, we did see something happen. So iron, observed the reactions that happened. H's took electrons. Oh, sorry, it's H pluses. Took electrons. And metal ions were formed. That's what I saw. Did it happen all by itself? Absolutely. Okay, I'm gonna go back. I'll show you one more time what I just wrote. If I take that iron, oh, look, and it got smaller too. The piece of metal got smaller. Put it in. Oh, I see bubbles forming. You could write that. I see bubbles. Here are the bubbles forming at a small level. So I see bubbles forming. And then I wrote down some other stuff. So I'm okay with however you write that. It doesn't have to be exactly what I write. You should be listening anyways. And now what I'm going to do is, because I got some stuff written for you, you should kind of get a feel for what happens. You're either going to write nothing, or you're going to write bubbles formed, or you're going to write something about those ions. And I'm not going to come back to this page for a minute. I'm going to let you see what happens and let you decide for yourself what to write. Okay, so I'm going to put magnesium in. Ooh, there's even more bubbles, right? And again, electrons going onto the H pluses, metal ions being formed. Lots of bubbles, electrons going onto the H pluses, making a diatomic hydrogen gas, and then metal ions falling off. And if you notice, check it out, when I take it out, this guy's even smaller. So this is what's happening to our metal electrodes within our voltaic cells. Okay, so now we're going to try nickel, and less bubbles, but it is working. Less bubbles, but it's working. Okay, so again, you write down the data. I'm not switching back. I'm going to go to lead now. Put lead in the hydrochloric acid. Ooh, even less bubbles. So I'm guessing it's less reactive. Oh, look, these guys are bigger for sure. For sure bigger. Okay, and then hence less reactive, less change in size here. Let's see about tin. Let's see if tin is more reactive. Put tin in. Oh man, tin is even less reactive. Look, only 4 little bubbles. Again, pretty big atoms. That the atoms got bigger, so I bet their their radius is bigger on the periodic table. And now zinc. So I'll put zinc in and see what's going on. And I see lots more bubbles. And again, something about bubbles formed. The bubbles are H2, something about the electrons moving, something about the ions formed. We've got a ton of room, so I'm giving you a lot of choices about what to write in there, okay? But I want you to think about it, and I want you to write stuff. And it says, how did you know if the metal react or not? Well, what did we see? What do we see? We had 2 that didn't react, and everybody else did. So what was the difference there? And I think you can handle that on your own. Flipping over to page 2. Page 2 looks like this. Beep. Now grab your reference table and use table J in complete. Did it react with? I want you to use silver. Use your data from 1 goes here. So you're going to copy over from page 1 right here and here and here. And then you're going to answer these questions about table J and try to figure out some stuff. And if you watch the video, the lecture video, you should be flying right through this. It's not all that complicated. Okay. And then we're going to ask some questions. I'm going to let you answer these. Notice on your original observation specifically the amount of bubbles formed. Rank the metals number 1 on the amount of bubbles formed produced when they were in HCl. So I'm not going to redo that, but you do have video of all of those bubbles. So if you have to go back and just rewatch right quick, you can do that and then rank them. Who had the most bubbles, who had the least bubbles. Okay. Talk about table J. Click on nickel and run the animation again. How many hydrogen ions react with 1 nickel atom? So I'll do that one again. I'll run nickel again. And let's just let me recheck the question. All right, I can read the question on my paper. How many hydrogen ions react with 1 nickel atom? So let's see. I have 1, 2, boom. 2 hydrogen ions react with 1 nickel atom. Okay. So 2 hydrogen ions react with 1 nickel atom. What does the nickel atom release? Electrons. How many? 2. What is formed from the hydrogen ions? H2. That would be hydrogen gas, or H2. Okay. Then, now we get to go back into these things. So click on step by step under the animation for nickel. This allows you to see the reaction that's occurring both reactions here. So I'm going to go to nickel. I'm going to hit step by step, and here are both reactions. So what I need you to do is write those down in that space on page, what would be 3, number 8. You have 2 lines to write 2 equations. I do not want to write them over because writing on the computer with the mouse is very difficult. You got them right there. You fill them in. It says the first reaction shows the entire reaction occurring in the solution. Okay, I see that. I see the metal, the hydrochloric acid reacting to form hydrogen gas and nickel chloride. So that's this top one. It says, although you cannot see the chlorine ions, they are present and will attract to Na2 pluses. How many Cl minuses will reach Ni2 plus attract? Well, I see Ni2 plus is a +2. How many -1s do I need? Well, look, the answer is right there. How many Cl's? Okay. It says the second reaction shows the ions we actually see in the animation. Cl- is considered a spectator ion and is not needed to show the transfer of electrons because nothing is changing there with its oxidation number. Which ion gained electrons? So we can run this one more time. I believe when I do it, which ion is gaining electrons? Right, that would be here's the nickel, 0, losing. Okay, so which one lost electrons is nickel 0. And next step, which one's gaining electrons? Well, that's going to be this H+. H+ is gaining them, and it's forming Ni +2. Okay? Now it says write the half reactions. What's the oxidation state of Ni? Well, Ni with no charge is 0, and it shows you right here that it's 0. And then Ni plus 2 is obviously plus 2. Does the oxidation state go up or down? From 0 to 2 is up. How many electrons were lost? Shows you right here, 2. This can be written as follows. Ni0 goes to Ni2 plus 2 electrons. When electrons are lost from one atom, they must be gained by another. So what gained the electrons? So let's go to next and show you that 2H pluses gained 2 electrons. The oxidation state of H plus is obviously plus 1. Oxidation state of H by itself, that's this guy over here, should have a 0 up top. Okay. Did the oxidation state go up or down? It went from plus 1 to 0, so it went down. I'm just going to hit next step and see if it shows it or not. Down here. I'm going to go back. Previous. Let's stay here then. Okay. Did the oxidation, it went down. Remember, this is how we remember reduction. Oxidation state is reduced. How many electrons were gained? Total of 2. Each needed for each nickel that was oxidized? Well, 1 for each. Wait. How many electrons were gained? Oh, so I think it's supposed to be 1 first, and then we're about to balance. So how many hydrogen ions are needed? 2. This can be written as follows. Why does this make sense that H2 formed instead of H? Well, nickel's given off 2, and we know hydrogen can only hold 1, so it's going to have 2 different hydrogen ions to scoop up the electrons. Okay, so I'm going to go to the next page of the lab. It says now it is your turn to write half reactions for the metals that reacted spontaneously. If you get stuck, this is a great place to ask for help and get a mini lesson. There are 6 metals that reacted. Choose 3 of them and write the oxidation and reduction reactions. So let's go back and just pick. If I remove this guy, I know I can do iron, magnesium. We already did nickel and lead. So let's do iron, magnesium, and lead. So you're going to write iron. Pop him in there. Boom, boom. It says, so under metal, I want you to write iron. I picked Fe. Number of electrons transferred, 2. Oxidation reactions. So I'm going to go back, go step by step. And here we go. The oxidation half reaction is this. So I want you to write this whole thing out where it says oxidation reaction for iron. Okay. And then it asks for the reduction reaction. So you can press pause, or if you have it written already, great. I'm going to go right to the oxidate or the reduction. This is the oxidation half reaction. We're going to go to the reduction. And there we go. The reduction half reaction is this. So in the same box there, you're going to write this under reduction. I'll give you just a second to do that. Now I'm going to move on to magnesium. Again, we're seeing the H pluses. Each one scoops up an electron, forms diatomic hydrogen gas, and off the magnesium ions go. I want to see just the, so for metal, I'm saying magnesium here. Number of electrons transferred, again, is 2. Oxidation half reaction is right here. The oxidation half reaction is listed right here. Take a second and write that out. Now I'm going to go to the reduction half reaction. If you need to go back and pause, that's fine. Here is the reduction half reaction is. There's the reduction half reaction. Now we're done with magnesium. Okay, now I'm going to take that. I'm going to go back to lead now. We'll do lead as Pb as the next third metal. Okay, how many electrons are transferred? Again, 2 electrons. Go step by step. Here is my oxidation half reaction for lead, Pb. Give you a second to write that. Here come my reduction half reaction. Here is the reduction half reaction. Now you need to write that. And then it goes on to conclusions. Each of the following is meant to help you summarize what you've learned. So electrons are gained or lost, oxidation or reduction. So under oxidation, are they gained or lost? We learned an acronym from that. I don't want to give it to you right now because you should know it by now. We know an acronym for telling me when electrons are gained or lost, and if it's oxidation or reduction. When writing half reactions, electrons should go on which side of the equation? Well, on this same page, we just wrote 3 different oxidation half reactions, and which side of the equation were the electrons on? The reactant side or the product side? It's going to be one for oxidation and the opposite for reduction. Oxidation state increases or decreases. So did the number charge go up or down on the oxidation half reaction? And did it go up or down on the reduction half reaction? You have all that material listed right here on the same page where you can just kind of look up at them and decide from the model what's going on. Use table J to complete the table. This is, I'm going to flip to it now because I'm on to the next page. This is where like AL would be like this. So it would go AL plus HF goes to. And we learned that when we have a lone metal, if the lone metal is higher than H, because this is going to act like a metal in this case because it's positive, Al, if it's higher than H, then yes, it will react. And if Al is lower than H, then it won't. And I can see one for sure that's lower than H because we know there's only 3 of them, gold, copper, and silver. Okay, so, and then rank these as far as the fastest. So we know the guy that's the highest up on table J is going to be number 1, react the most fast. And then we know that AU isn't going to react at all, so we know he's going to be a 5. I'm going to let you play with table H to figure that out. I'm sorry, that's table J, my bad. And then here's a reaction. Will it occur spontaneously? So again, is Na above the H? Now notice here, instead of me writing it Na plus H2SO4, this is the same thing, man. I just changed the order of which way I wrote the ingredients. So is Na above H on table J? If it is, it will be spontaneous. And that's the answer here. And then what is oxidized? So now you need to go ahead and put in your oxidation numbers. I'll give you a hint. And then you got to do it again over here. You know, this is going to be 0. This is still going to be -2, and Na is going to be a +1. Okay, figure out who's being oxidized and who's being reduced, and fill out your half reactions. Okay. If Na and CO reacted, which would be oxidized and which would be reduced? So this is code for saying which one's higher. The one that's higher on table J will always be oxidized. He's the most reactive, so he's going to give up his electrons. So which one's higher, Na or CO? Whoever's higher, that answer goes here. The other one goes here. And how did you decide your answer? I just kind of walked you through that. You just tell me that it's higher on table J. Okay. And then here, will these substances, will they recur spontaneously? So this is Na higher than H? And is Mg higher than H? If so, whoops, I did that one backwards. Notice they're both written different ways. So if H2 is higher than Na, it will go. If Mg is higher than H, it will go. Notice they're opposites because this guy, this salt, is not an acid yet. It doesn't have the H, where this one does. So you want the bonded metal, or the unbonded species, to be higher than the bonded species. So this one is this one higher, and then this one is this one higher. Okay, and you got to make sure you can keep that straight, and that's right from video 5. Then Li and O, these are super reactive. Li is the most reactive metal, and O2 is right up there. Will it react? Absolutely. We know if I take lithium and put it in oxygen, it's going to go. And then oxidized, who's higher? And I believe, if I remember correctly, this is on the metal side, but this is on the non-metal side. So who's higher? And I won't mark you wrong on that particular question. Just do your best to answer that out. I want you to think. And with that, you're done with the lab. So make sure you hold on to a paper copy of this. Um, definitely um, make sure you answer all the pieces, even if I didn't, because I showed you all the different reactions. You can go through and watch those pieces over again if you need to. Okay. And there's no actual CEI, but I need you to hold on to this and eventually get it for me. Get it to me somehow when we all get back together, so that I can give you guys your formal lab minutes. And I know that you did it. Even if you end up taking pictures of it, you can do that. Okay, so with that, we just went through this whole lab, and you guys got to see all the simulations that just broke down the half reactions. And the reason why I like this so much is it really shows you what's going on, where these hydrogen ions come floating in, and the electrons from the metal jump to those hydrogen ions, and then it makes hydrogen atom and hydrogen atom, and then they bond together because we know hydrogen is diatomic. That's what gives off the bubbles. Okay, and there's all the different half reactions happening all at once, and then the ions happen and fall off. So this is what's happening at the anodes of all the voltaic cells, where the ion electrons are coming from the solution. It doesn't always have to be an acid, by the way. This is also showing you what's going on in table J with just the activity series. Um, but in voltaic cells, it won't necessarily be an acid, but there's going to be ions of some sort that can take the electron, or that give the electrons, and the electrons take off. So it's actually not perfect. I lie. It's not perfect. This is just acids. And but in the voltaic cells, what happens is um, electrons are provided from this solution here and makes metals. The metals make ions. Yeah, the metals make ions, and the ions fall off like this, and the electrons go through the wire instead of H2 gas coming off. It's tough to see, to understand without seeing it, but it's very similar. So instead of H2 gas coming off, the electrons go up the wire, and these metal ions start falling off. So very similar. Anyways, and the simulation in that part works fabulously. So with that, there's your lab. Hope it all goes well. Email me with any questions. Let's go look. Did not. I will stop it.